So in this video, I'm going to try and explain to you the importance of the oh, that's a bit thick. Can I go down? That's better. Of the chi-squared distribution. So hopefully you're already aware of what the chi-squared distribution is, or at least have some idea. Ideally, you would know what the PDF of the chi-squared distribution is and what the MGF of the chi-squared distribution is, and the aim of this video is to explain why this distribution is so important to statistics. So, it's because the chi-squared distribution ends up being the way that the sample variance is distributed. It ends up being the sampling distribution of the sample variance. When you are drawing, and this is the caveat, when you are drawing from a normal random variable. So, but then, as always with statistics, a lot of theorems that, strictly speaking, only hold true for normal random variables, they end up still being vaguely true, even when things aren't normally distributed. So a lot of the statistical tests that are done in statistics, even though they're designed for things that are being drawn from true normal distributions, even when they're being done on things that aren't being drawn from true normal distributions, they still end up being sensible tests. And we're not going to go into that in too much detail here. We're going to focus on the perfect world where we're truly drawing from normal distributions. So here's the idea then. So let's say we've got x, in fact xi, that are all being drawn, and we'll start simple. So we'll say they're being drawn from the standard normal distribution, so from normal 0, 1. And we'll have I is equal to 1, 2, all the way up to n. So we're sampling n times from the standard normal distribution. And these are all IID, so independent, that's important. So we've got n independent draws from normal 0, 1. And then, let's firstly just revise the sampling distribution of the sample mean for this setup. So to take the sample mean, and I'll call the sample mean as a random variable x bar, it's literally just you take the answer to each of the n draws, so x1 plus x2 all the way up to xn, you add them all together and then you divide through by n. So you add the n random variables together and divide through by n, and that will give you your sample mean. And then we can ask, how is this distributed? Because of course, you know, if you draw n times from the standard normal distribution, if you do that experiment twice, so you draw n times and then you draw n times again, you're going to get different things on those two draws, or you're very likely going to get different things, and the sample mean will also likely differ between those two experiments. So there is then a distribution which tells you the probability of getting a certain value of x bar, and that's what I'm talking about when I say the sampling distribution of x bar. And it will be given by, if you add these n normal 0, 1 random variables together and divide through by n, we want to know how is this going to be distributed. So hopefully you know this already. So when you add a bunch of independent normals together, you get another normal. So all we need to know is what is going to be the mean value and the variance of this, and we can just take expectation of this, and then by the linearity of expectation it ends up being the expectation of this plus the expectation of this all the way up to the expectation of this over n. These all have the same expectation, which is 0, so we overall get 0 added together n times divided through by n. So we know what the mean is going to be. X bar is going to be normally distributed with mean 0, and then we just need to know the variance. So again, we can take variance of this whole thing, and then because they're all independent and therefore their covariances are 0, it becomes, well, first let's pull out the constant. When you pull out a constant of variance, it gets squared, so you'll have 1 over n squared times the variance of this plus the variance of this all the way up to this. They all have the same variance, 1, so you get 1 added together n times, which is n, so you get n divided by n squared, which is 1 over n. So that's the distribution then, the sampling distribution for the sample mean. It's normal 0 with variance 1 over n. Standard deviation 1 over the square root of n. So now we can ask the question, what about the sampling distribution for the sample variance if I draw n times from normal 0, 1? I'm trying to think of some good notation for this. So firstly, we're going to take a simpler setting. I'm going to do something that we wouldn't normally do when we calculate the sample variance, which is I'm going to assume that we use the population mean, that we know the population mean is 0, and we use that in our calculation of the sample variance. So what I mean by this is we would do x1 minus 0 squared plus x2 minus 0 squared, and I'm going to drop writing the minus 0 plus all the way up to xn minus 0 squared. So we take this sum and we'd use that as our sample variance. However, that's not what we normally do. I'm doing this because it's just a simpler question to answer initially. Of course, normally when we take and of course we then end up dividing this through, and in this case we probably end up dividing it through by 1 over n rather than using the Bessel correction of 1 over n minus 1, and actually we'll explore later, if I remember, more why the Bessel correction is such a sensible thing to do. So this is the sum not yet divided through by the n. So that's not what we would normally do, however, to calculate the sample variance. Normally what we would do is we'd calculate something that I'm going to call SXX. Some people don't necessarily call it this. This is notation that's used commonly in simple linear regression. I like using it here as well because this sum that I'm about to write down is the same thing in this context as it would be in simple linear regression, and just because there isn't a good symbol for this, so I like giving it a symbol, so I use usually SXX. So it would be the sum from I is equal to 1 to n of xi minus x bar. So you wouldn't know, you wouldn't know the actual true mean. Instead, when you would calculate the sample variance, I've drawn from this distribution n times, I get some sample. We'll put it up here, little x1, little x2. So these aren't now random variables. These are the actual sample that I'm writing here. I get my sample, and if I'm going to calculate the mean, I would just add these all together and divide through by n. And if I'm calculating the sample variance, I wouldn't do this. I wouldn't just square each of them and add them together to calculate the sample variance. No, what I would do is I would take each of them, subtract off the sample mean, x bar, and then square it. And then, of course, I'd have to divide through by, really it should be n minus 1 rather than n, the Bessel correction. So the naive thing to do would be to divide through by n. That's what we kind of learn to do in school. But then when we go to university, we learn that that's not actually a very sensible thing to do. There's a much more sensible thing to divide through by, which is n minus 1. This is called the Bessel correction. Replacing n with n minus 1, that's known as the Bessel correction. It means that this estimator for the variance is unbiased, and it is there's, in my opinion, an even better reason for why you do this, which is what we're about to discuss, the fact that this comes out chi-squared distributed, but not with n degrees of freedom, with n minus 1 degrees of freedom. So it's sensible to divide through by the degrees of freedom rather than the degrees of freedom plus 1, which is what you would be doing if you divided through by n. And that becomes very, very important when we consider like t-tests. You need, when you remember the definition of the t-distribution, it's normal 0, 1 divided by the square root of a chi-square distribution divided by its degrees of freedom. And the reason that's such an important distribution is because often in statistics we take a sample mean potentially corrected so that its mean is 0, and then divide it through by the sample variance, which is then going to be chi-squared distributed with n minus 1 degrees of freedom. But then we do need to be dividing through by that degree of freedom in order for it to actually come out t-distributed. So you don't want to be dividing through by the incorrect thing. You want to be dividing through by the degrees of freedom of this thing here. And so as I say, I hope that will become more clear as we go on. So where were we? So this is kind of like if we had the perfect world, we already knew the mean, we could calculate this as our sample variance, but of course this is what we would really calculate for our sample variance. So now this will denote s squared. That does have standard notation. Once you take sxx and divide it through by n minus 1, that's denoted s squared for the sample variance. So this is a different thing. You know, if I want to work out this thing's sampling distribution, it's different to this thing's sampling distribution. And the reason we're going to begin with this one is because it's simpler than this one, and it will help us work out this one. But just to emphasize, you know, this thing here, really you could replace that with x1 plus x2 plus all the way up to xn over n there. So trying to work out what this algebraic combination of random variables, how this thing is going to be distributed, you can appreciate that it's quite a complicated task here, but there is a wonderful trick with MGFs that's going to allow us to understand how this SXX is distributed. And just a bit more, actually, the name for this thing, this is the sample corrected sum of squares. If you like, this thing that I've written here, this is like just the sample sum of squares, or just the sum of squares, whereas this thing that I'm calling SXX, this is the sample corrected, let me just take that away, sum of squares. Sample corrected because we're correcting by the sample mean now. Right, so let's start off with how just this sum of squares would be distributed. So because, and this is where I'm hoping that you have some knowledge already, so because each one of these random variables, x1, x2, all the way up to xn, they are all independent normal 0, 1, then we've just got the sum of n squared normal 0, 1 random variables, and so we know how this is distributed. This thing, I don't know what to call it really, we'll call it y. Y is going to end up chi-squared distributed, I love the symbol chi, with n degrees of freedom. The question now is, so that would be the sampling distribution then. So this is the start of the answer of the importance of the chi-squared distribution. It would be the sampling distribution, or it would be related to the sampling distribution. Of course, we need to multiply through by 1 over n here to get a sample variance. And n would be the right thing to divide through by here because the fact that this sum is chi-squared distributed with n degrees of freedom. So you always really want to be dividing through by the degrees of freedom when you're calculating a sample variance. In this case, the degrees of freedom is n. It's going to be chi-squared distributed with n degrees of freedom. But forget the 1 over n for now. You know, this thing is, bar a constant, it's the sample variance. So we've got then the distribution, or something very much so related to the distribution for our sample variance, and that's the start of the answer as to why the chi-squared distribution is so important. If you're sampling from normal 0, 1, then this sum that is very related to the sample variance would be chi-squared distributed with n degrees of freedom. However, we now want to do better, because actually, when we calculate the sample variance, we're going to be using this, the sample corrected sum of squares, rather than just this sum of squares. So let's now try and figure out then how this thing that I'm calling SXX, how is this going to be distributed? So how are we going to do this? Let me just remember how you do this. So there's some knowledge, this is important. So I am not going to fully prove this to you. I'm going to give you what I hope you're going to find a satisfying answer. But I'm not going to be able to fully prove this because I don't actually know the full proof myself. But I'm going to tell you the assumption that we're going to work on, the bit of knowledge that I'm just going to tell you and you're just going to have to accept, which is that x bar and this thing, SXX, they both have sampling distributions, and the miracle that you're going to have to accept is that somehow they come out independent of one another, these two random variables that are constructed out of the same random variables. So they're all being constructed out of x1, x2, all the way up to xn. So even though they're being constructed out of the same n normal 0, 1 random variables, somehow these two things, this and this, end up independent from one another. And as long as you accept that now, I can give you the argument as to why this thing ends up chi-squared distributed with n minus 1 degrees of freedom. So, as I say, I don't know how you prove this. I just accepted it as one of the miracles of statistics. Hopefully one day I will know how to prove it, and I will make a video to explain that to you. But for now, we're just going to accept it, and we're going to use it. And I still find this explanation very satisfying, even though it's not complete, because we are just going to take this as given. So, we need to, what are we going to do next? I think we actually are going to start with this one and decompose it into this. So let's take this sum of squares. I think this is the right thing to do, and this will be a work in progress. I personally prefer doing videos like this where I'm not completely scripted, because I think they're more natural, and I actually love watching people do mathematics spontaneously and watch them actually genuinely think. I find that more interesting and more useful than watching a beautifully scripted performance. I like beautifully scripted performances as well, but I really, really like watching people do things on the spot. So we might have to adjust our strategy here, but that's good. That's not necessarily a bad thing. So, we're going to start with this one, and we're going to do the classic trick in mathematics, which is we're going to add and then subtract the same thing, so we're effectively adding 0. So this is what I'm going to do. I'm going to take xi, I'm going to minus x bar, and then I'm going to plus x bar. I think this is a good strategy to do. So you'll hopefully appreciate that I have not changed this. This thing, by the way, we know how this is distributed. This is distributed chi-squared with n degrees of freedom. So now what we're going to do is we're going to push a bracket around this and then expand it into two separate things. So we'll get sum from I is equal to 1 to n, and then we'll get xi minus x bar squared plus, and then we'll get 2x bar xi minus x bar, so that's the cross term, and then we'll get plus x bar squared. So then we need to do the sum, and you'll notice that this thing here is what we want. This is our SXX, so we'll keep that. So we'll have our SXX. Then this bit here. Now, this is, with respect to this sum, a constant. It's just x1 plus x2 plus all the way up to xn over n. So this can be pulled out. And then you've got the sum of xi minus x bar. Now think about what that's actually going to give you. If you actually wrote that all out, you get x1 plus x2 plus all the way up to xn minus n lots of x bar. N lots of x bar is then just x1 plus x2 plus all the way up to xn, because the n on the denominator cancels with that n. So you've just got x1 plus x2 all the way up to xn minus x1 plus x2 all the way up to xn. So this ends up all going to 0 when you do that sum. So that bit goes, and then we just get plus n x bar squared. And that's what we want. Excellent, good. So now what we're going to do is firstly just have a look at this here. So x bar, we know how x bar is distributed. It's distributed normally 0, 1 over n. So if we now consider this the square root of n x bar squared, so when you multiply by a constant, if you think about what this is going to be, this is still going to be normal. If you take a normal and multiply it by a constant, you still get normal. The expectation is not going to change because the constant just comes out and you get that it's the expectation of x bar, and the expectation of x bar is 0, so 0 times that constant is still 0. The variance is then going to be the square of this times the variance of x, so we'll get n times x. So this thing, the square root of n times x bar, this is going to be normal 0, 1. How beautiful. And therefore when we square this thing is going to end up chi-squared distributed with 1 degree of freedom. So now you can kind of see how this is all going to work. This thing on this side is chi-squared distributed with n degrees of freedom. Then we've got this thing, which we don't yet know how it's distributed. Remember, we're aiming to show that it's chi-squared distributed with n minus 1 degrees of freedom. And then we've got it plus something with chi-squared, which is chi-squared distributed with 1 degree of freedom. And literally, we need to give an argument as to why, but the degrees of freedom on this side add together so that you get n. This is also going to be chi-squared distributed with n minus 1 degrees of freedom. This is chi-squared distributed with 1 degree of freedom. They literally add together to then give something that's chi-squared distributed with n degrees of freedom. But we need to give an argument as to why that is. So we do it with MGFs. So because this thing is equal to this thing, therefore the MGF of this thing is equal to the MGF of these two things. When you take the MGF of one random variable plus another random variable, it just becomes, oh well, importantly, if they're independent. So if you take the MGF of one random variable plus another random variable where they are independent, and remember that's the assumption that I said we're just going to assume that x bar and sxx are independent of one another. So if we accept that, then this on this side is the MGF of this thing times the MGF of this thing. We know what the MGF of this thing is because it's chi-squared distributed with 1 degree of freedom. Hopefully you know the MGF of the... Do I know the MGF of the chi-squared distribution? So I think... I hope this is right. So I think if you have, let's say, U, which is chi-squared distributed with n degrees of freedom, then the MGF of U is equal to 1 minus 2t to the minus n over 2. Yep, that I think is right. So the MGF of this one is going to be 1 minus 2t to the minus a half. So that's the MGF of this. Then we have times the MGF of our thing that we're really interested in, this sxx, as a function of t. And then it's equal to the MGF of the thing on this side, which we know is chi-squared distributed with n degrees of freedom. So that's 1 minus 2t to the minus n over 2. So now all you do is literally multiply through by 1 minus 2t to the power of a half. And that will cancel on this side. So we then get that the MGF of sxx is equal to, and then we'll get 1 minus 2t to the minus n over 2, and I apologise for my writing going off a little bit, times 1 minus 2t to the half. And let's now just combine those together. So we'll this becomes then 1 minus 2t. So that we want to keep the minus out because that's that's there in the standard form. So we'll get minus, the n still there, but then we need to make this minus so that it will cancel with this minus. So we'll get minus n minus 1 over 2. So therefore this is the MGF of a chi-squared distribution with n minus 1 degrees of freedom. And then another thing that we are not at all going to attempt to prove here, which is the correspondence between MGFs and distributions. So the fact that this thing has this MGF then means that this thing is chi-squared distributed with n minus 1 degrees of freedom. Again, I'm not about to prove that. That's, I believe, some quite serious analysis. Again, I don't know. I haven't ever done a mathematical statistics course. So there we go. So that was actually the main thing I wanted to show you in this video, that this sample corrected sum of products, this thing, and we'll do this in red. I've been writing a lot in white, but let's change colour now. This thing is chi-squared distributed. I really do love the symbol for chi. Chi-squared distributed with n minus 1 degrees of freedom. Although, actually, I shouldn't probably say that. Like, it looks a bit like a swastika, the one that I've just drawn there. Let's get rid of that. No, I don't love that symbol. So, sxx is chi-squared distributed with n minus 1 degrees of freedom. That's the main thing that I wanted to teach you in this video and show you at least some of an explanation as to why this is. As I say, there are things that we haven't proven here. We haven't proven that these two, that sxx and x bar, end up independent, and that is quite crucial in our argument. We also certainly have not attempted to prove the correspondence theorem between distributions and MGFs, the one-to-one correspondence. But if you accept those two things, then this is still something of a nice argument as to why this thing ends up chi-squared distributed with n minus 1 degrees of freedom. And of course, this isn't quite the sample variance. You then would divide it through by n minus 1. And here's another explanation as to why that is such a clever thing to do, because you are dividing through by the degrees of freedom by which this sample corrected sum of products is chi-squared distributed. And we will talk in a upcoming video about the importance of the t-distribution in statistics, and you will see that it is really important that when you take your sample variance that you do divide through by the correct degrees of freedom in order that the test statistics that we commonly build will end up t-distributed. So with that, I will probably finish this video. I hope that you have gained something from that. This video was overall on why the chi-square distribution has importance in statistics, and the answer is that it is very much so related to how the sample variance is distributed, where this is our definition of the sample variance. Yes, we have this constant here, but the thing on the top, the main bulk of what the sample variance is, ends up chi-squared distributed with n minus 1 degrees of freedom. At least it does if truly we are drawing from normal 0, 1 distributions. In fact, actually, just before we finish, I might say something about what happens if we are drawing from a more general normal distribution. So I'm not going to go on to distributions that aren't normal, but we could generalize from, we could go beyond just standard normal. So let's say now that we have xi, which is normally distributed. How far should we go? Just let's firstly start off, keep the mean 0, but let's just make the variance something general, and then we'll do the full thing and put in a general mean. And let's now think about how x1 minus x bar, sorry, xi minus x bar, let's think about how our sxx is going to be distributed. So this is sxx in this case. So how are we going to fix this up? And I'm just wondering whether, is this as easy as I thought it was going to be? I think it is still. Yes, so let's think about how x bar is going to be distributed. So they'll be distributed normally, the mean will remain 0, the variance will then be sigma squared over n. Right, so if we now take this thing, and I think we need to divide everything through by, yes, we need to, so let's take sxx and divide it by sigma squared, then the other side being divided by sigma squared will be sum from I is equal to 1 to n, and then we'll pull the sigma squared into the square, and then we'll get this, xi minus x bar squared. So this is a great big sum. I've divided everything by sigma squared, and then I've pulled the sigma for each one into its square, so it's become this. And now what we can do is we can think of this as sum from I is equal to 1 to n of xi over sigma minus x bar over sigma squared. And now why is that such a clever thing to do? Well, now, how is xi over sigma distributed? It's distributed normal 0, 1. And how is x bar over sigma distributed? Well, again, we just need to divide the variance now by sigma squared, because remember, multiplying by constant, you multiply the variance by that constant squared, so we're multiplying by sigma, 1 over sigma rather, so we'll be multiplying the variance by 1 over sigma squared. So x bar is now going to end up normally distributed, normal 0, and then it's going to be 1 over n. And you see now that we've effectively reduced ourselves back to the first situation, because we've got things that are, if we replace this with yi, say, we'd have things that were normal 0, 1 distributed, and then we'd have their means, which are going to be normal 0, 1 over n. So if, in fact, let's just do that. Let's call this now yi. So xi over sigma we'll call yi. They're all normal 0, 1. And if you think about what x bar over sigma is, that will be x1 plus all the way up to xn over n sigma, but let's pull the sigma up into the numerator and then divide through all those things by by sigma. So you'll then get x1 over sigma plus x2 over sigma plus all the way up to xn over sigma. So you'll get y1 plus all the way up to yn over n. So literally you've reduced it back to the first problem of being this sample corrected sum of squares for normal 0, 1 distributions, where these y random variables are going to be normal 0, 1. So that means that we know how this thing is going to be distributed. We've just shown that it's going to be chi-squared distributed with n minus 1 degrees of freedom. So now SXX isn't chi-squared distributed with n minus 1 degrees of freedom, but SXX over sigma squared, that thing is going to be chi-squared, what am I doing? Chi-squared distributed with n minus 1 degrees of freedom. So, again, there's a constant off. You're going to have to alter this distribution slightly. You're going to have to multiply it through by a constant, so it won't be perfectly chi-squared distributed anymore, but it's just going to be a constant multiple of a chi-squared random variable with n minus 1 degrees of freedom. So the sample corrected sum of squares is still very much so almost chi-squared distributed with n minus 1 degrees of freedom. And then let's finish by doing the final one, so where we do xi is normal mu sigma squared. So it's a similar thing, we want to just alter it slightly. So let's again think about, so we'll want to do the same thing, we'll want to do SXX over sigma squared, so that we've got sum from I is equal to 1 to n of xi over sigma minus x bar over sigma. Yep. Now, if we think about how those things are going to be distributed, so xi over sigma is so its mean is going to move now. Its mean is going to become mu over sigma, and its variance will become 1. So we now just need to do something about this mean. We'll forget x bar for the moment. We'll deal with that in a moment. So what we need to do is correct its mean to make it normal 0, 1 again. So again, we're going to do the trick of adding 0. So adding and subtracting the same thing. So sum from I is equal to 1 to n of xi, and we're going to subtract off mu over sigma and combine that together. So we'll have to add back in mu over sigma. But actually, I'm going to stuff that in with the x bar, because the x bar is going to need to be corrected as well. So we'll put that here, minus mu over sigma squared. So hopefully you appreciate that I have just added and subtracted the same thing. So we've got minus mu over sigma here. These two minuses make a plus, so this cancels with this. So now, if I call this thing here my yi, then yi is going to be normal 0, 1. So standard normal. Now I just need to convince you that this works as well. So if we think about what x bar minus mu over sigma is, so x bar is just x1 plus all the way up to xn over n. So I'm going to bring that mu into that fraction, so we'll get now minus n mu. And you see what I can do is I can give one of... sorry, I've just got rid of my mu. I meant to press this. So now what I'm going to do is I'm going to split this n lots of mu between these n random variables so that each one of them has a minus mu, because I'm trying to make them into the y's. And then I'm going to bring this sigma up. It's down here at the moment. We're dividing this whole thing through by sigma, so it will end up down here. But we're going to bring it up into the numerator as well, so that what we'll end up with is x1 minus mu over sigma plus all the way up to xn minus mu over sigma. And I apologise, my writing's going off. It always goes off as we go towards the end of the page, or to the bottom of this wonderful device. Divided through by n. So then you see that we've got y1 plus all the way up to yn divided by n, and those are all normal 0, 1. So we've got the mean of the normal 0, 1s. So literally we are taking the sample corrected sum of squares for these things that are now being drawn from normal 0, 1, and we know how that's distributed. So that will be distributed chi-squared with n minus 1 degrees of freedom. So basically, for the general normal distribution, normal mu sigma squared, if you are taking n independent draws from that, then if you calculate this statistic sxx over sigma squared, that thing will be chi-squared distributed with n minus 1 degrees of freedom. And then sxx, this sample corrected sum of squares, this is very related to the sample variance. All you need to do then is take this thing that, oops, I didn't mean to do that, take this thing that is chi-squared distributed with n minus 1 degrees of freedom, multiply through by this true variance. And you might wonder, isn't that going to be a problem, because we don't necessarily know what that is in statistics? But actually it ends up all going away. You'll see, like, often we're far more interested in test statistics that will end up t-distributed, and you'll see that this thing, this sigma squared, will end up cancelling on the top and the bottom, so it doesn't matter that we don't know it. We're just kind of building up to understanding t-tests in this video. We firstly need to understand the significance of the chi-square distribution in statistics to then understand the significance of the t-distribution in statistics. So basically, if you take this thing, multiply it through by sigma squared, and then divide through by n minus 1, you will get the sample variance, the Bessel-corrected sample variance. And you can see that that is just a constant, therefore multiplied by something that is chi-squared distributed with n minus 1 degrees of freedom. And as I say, for this to be absolutely true, you really do need to truly be drawing from a normally distributed stochastic process independently. However, in more advanced parts of statistics, they will discuss how this concept generalizes beyond just drawing from the normal distribution, and how things that we're going to see about how if you're truly drawing from normal, then certain test statistics will truly end up t-distributed. Even if you're not truly drawing from normal, t-tests are a sensible thing often to do because the thing is close to being t-distributed. So with that, we will finish this video. I hope you've enjoyed that, and I hope you've learned something about the chi-square distribution and why it might be such an important distribution in statistics. It is the sampling distribution of the sample variance, or it is almost the sampling distribution of the sample variance when we are drawing from normally distributed stochastic processes.